right, so for today, come on, pen. We're going to continue with Allylic Bromination. I knew that was going to happen. And it is what, 27. So what we talked about up to this point, we've been talking under the umbrella of synthesis, and well, we're going to see. I'm not going to add the application part yet. Synthesis of alkyl halides and the methods we've talked about so far. We talked about allylic bromination. And then we're also going to talk about alcohol conversion. To alkyl halides. All right, so we're going to finish up allylic bromination today, and then kind of introduce alcohol conversions. On Monday, we'll do more of the alcohol conversion, and then on Wednesday, we'll take the exam. So for right now, the exam topics are pretty clear cut. We got stereochemistry and all the topics we talked about with that. And then alkyl halide synthesis. So those are the two big topics, and the details are obviously in the notes and what we talked about, but those are the two main topics. All right, so let's jump right back in to right here. I'm gonna have to cut this out, but it says, for the following two reactions, draw all possible products. And for reaction one, propose a mechanism for their formation. So we actually are gonna talk about, we're actually gonna do both and do the mechanism for both. And then we're gonna do that last problem, right? So if we look at number 3, reaction 1, how many potential products can we predict from that based on what we know from what we talked about on Wednesday? And how do you go about predicting the number of products?
Isn't it like 2 to the power of the number of chiral centers?
Well, that's a different topic. That's for,
oh, okay.
It's okay, but it's the same idea, because it's the number of allylic sites times 2. But you're thinking about how to predict the number of stereoisomers.
My bad.
But right here, so let's back up. Where are the allylic sites in this molecule? What does that term allylic mean? There's no sense in saying it if we don't understand the terminology. So what does that term allylic mean?
Next to an alkene.
Adjacent to an alkene. Great. So we got a site right here and a site right here. Is that right?
Yes, sir.
Both of those are allylic carbons. So when we go through the mechanism for this reaction, when we get to the propagation step, those are the carbons that are going to get abstracted. So how many products are we going to make? Because we know we're going to make at least 2 radicals in propagation, because we got 2 allylic sites.
4.
4 products. That's exactly right. We'll have 4 total products. And with this reaction, we're going to talk about another another aspect of this, which is the product formation, like which one forms the fastest, which one is the most stable. We're going to talk about that too. All right. So let's take this. I'm going to cut it, because we'll come back up here and draw the products in, but I'm going to cut this out. So we'll have room to work through this and not be trying to squeeze something into that little small space. All right, so I'm gonna paste that down here. On this page. All right. Make that a little bigger. So first step is what? If we're talking about the mechanism now, we're not talking about which products are going to be formed. We're going to go through the mechanism to show all that. But what's the first step in any radical mechanism?
Initiation.
Initiation. Right. And if you go, I have a video that I'm gonna send along with the videos from Monday, that goes through this radical process. It's a real simple video, but it'll refresh you. So the initiation, we said, was MBS getting cleaved. Is that right? And this step, I'll normally, like on the exam, I'll give you the MBS part. I don't want you to have to like think about that part, because that's not the important part, right? The important part is the propagation steps where all your radicals get made. So this is MBS. I'm gonna shine light on that, right? That's H nu. I remember that from part one of, actually part two. Oh, no, part one of GChem, energy of a photon. H is Planck's constant, and the nu, lowercase Greek n, is the frequency of the radiation. Y'all remember that? No? Okay.
No.
Really? Y'all don't remember this equation? E equals H nu, energy of a photon?
Yeah. Yes.
Yeah,
Yes.
I knew that. Come on now. I know y'all remember something from somebody's class. All right. So we got that. So that's what the H nu is. It's the energy for that radiation. Normally we do this under UV light because that's really powerful. That's a really powerful type of radiation. Right. So it's enough to cleave, enough to give enough energy to cleave that bond. So we're going to get this as a radical plus a bromine radical, right? So we're not really worried about that step. What we do care about is the propagation, because that's where all my new radicals get formed. And every radical I make in propagation is going where to finish the reaction. What's the final step? Anybody?
Termination.
Termination. Good. That's my start material. I'm gonna go ahead and copy that so I don't have to fight with it, right? So everybody of the same mind in this case, that there's a hydrogen here, and that's my allylic hydrogen. And then there's also allylic hydrogens here on this carbon. Right? And don't panic if I leave these lines blank right here, right? They're understood to be CH3s. All right. So we might need to go back and refresh skeletal and line forms, also structures, to kind of bring yourself up to speed on that. But if I leave it blank, it's still understood to be a CH3. The end of every line is a CH3, and every vertex, unless it's otherwise noted, is a CH2. All right. So we're going to start on the right side. So that plus what? What's going to come in and abstract that hydrogen?
Bromine.
Bromine. Good. The bromine radical that I made up top. All right. And it's going to do a homolytic bond cleavage. I'm just going to draw that arrow like that. So the CH bond we're breaking in half. And we're doing it homolytically, meaning one electron is leaving with hydrogen and one is staying back on the carbon that the hydrogen was bonded to. All this stuff is from part one. Homolytic, homogenic, heterolytic, heterogenic, all those bond forming and bond breaking processes. That's all this is. The only thing that's new is the reaction we're looking at. Right? I mean, I gotta shrink that so I can have room. All right, so that's the first part of propagation. And then over here on the other side, let me see if I can paste that. Come on, baby. Perfect. I'm gonna have a radical at this site. I'm gonna make it in pink. I'm gonna have a radical right here on that carbon. 1 electron plus what?
Hydrobromine.
I heard it, but it was kind of faint.
Plus bromine.
Hydrobromine. Can you hear me?
Yes, go ahead.
I said it was the hydrobromine. That's
Yeah,
I just
HBr.
wrote
Yep.
it.
Good. Are y'all following that?
Yes.
All
Yes.
right. And then we're going to take the same compound. Nope, don't want that. I want the real thing. Same compound, but on the other end, remember these abstractions. You're not going to have two abstractions of the same molecule. You're going to do an abstraction on one, and you got another molecule also floating around in solution that you're going to abstract from. All right, hopefully that makes sense. Because you're not going to make two radicals in the same molecule. Well, where this little crop dust is flying to, you need to go on somewhere. Got a little small airport close to here, so. All right, so these are the hydrogens that I'm gonna mess with this time. So that plus bromine, same thing. It's gonna be an abstraction where you break the CH bond, give one electron back to carbon, one is leaving with hydrogen, and then bromine is coming in, right, to grab that hydrogen. So it's facilitating that process of abstraction. That's why bromine is the initiator, because it initiates the bond breaking process in propagation. All right, so then we're going to take, I'm going to copy that. Actually, yeah, nope, I'll just put the other one back. So now where's my radical going to be? Right here, isn't it? On that carbon. Is that right?
Yes.
Mm-hmm. And there's going to be plus HBr, right? Yes.
Right.
All right, now, what do we know about those allylic radicals? Somebody help me with that part. What do we know they do, and why do they do it?
Resonance.
They can do resonance. And what's the purpose of it doing resonance? Anybody? Or you can answer. I think that was you. Was that you, Quenisha or Quinetta?
Quinetta.
Yeah, I can't see, but I know your voice though. Why does resonance even happen?
Stability.
Take that one electron and spread it out over multiple atoms. And the way that you share electrons is by overlapping orbitals. So that, let me give you a kind of a bird's eye view of this allylic system. All right, so I'm gonna write this in a different color. So that radical, it's like here, it's sitting in a p orbital, that one electron. And then you got p orbitals right here on this, making up that pi bond. So as long as those three p orbitals are in a row like that and not separated, they can share electrons. And so that's why I can put resonance arrows in here, like that. Let me not do that. That's why I can put those resonance arrows in like that, because those orbitals are aligned in such a way that they can talk, they can overlap, they're overlapping, right? So they can share electrons between them. That's how resonance happens. You have two or three atoms close enough to one another that the orbitals can overlap and they can share electrons. And the more you can spread those electrons out, the more stable that molecule is, right? The more delocalized the electron density is, the better, right? So that's what resonance does. This is delocalization. Right, and I know this is heavy from part one, right? Because resonance is a big part of learning part one. So anytime you have it can be a radical, it can be a cation, it can be an anion, it doesn't matter. If it's allylic, it's going to do resonance in order to stabilize either the charge or that unpaired electron. Right, so both of those molecules up top, both of those radicals can undergo resonance. Everybody agree with that?
Yes.
Yes.
I'm gonna move this over here so I can have room to draw my radical, my resonance form. All right, so for this top one, and there's always a double-sided arrow when you're indicating resonance, because the resonance forms are interchangeable, right? You can go from one to the other. And it's constant. Although some resonance forms are more energetically favorable than others, it's still interchangeable. So how would I show this radical up top? Rearrange it. Sorry about that. I'm trying to kill a fly. How would I show it? What would the arrows look like to rearrange that radical?
On the double bond to the right.
So we know the double bond is going to split in two like that. That's a given. So the two atoms in the double bond are always going to react they're always going to act the same way. You're going to take that pi bond and split it between those two atoms so that each one gets an electron. And then the electron here is going to get shared with this one, right? So now your pi bond is going to be between those two carbons like that, and then you're going to have a radical here. All right, anybody not see that? So that's one of my resonance forms. We're going to label them. So I'm going to call this one A and that B. We're not going to have the same confusion like we had the other day when I went crazy with the alphabet. All right, what about this one down here? What do you think? It's an allylic radical just like the one up top. So what do you think is going to happen? Is it going to do something different?
No, it's gonna do the same thing.
Is it going to take the electron to the pawn shop and drop it off? No, it's the exact same system. Well, it's the exact same type of system. So it's going to do the exact same thing, right? It's going to pass an electron here. One electron is going to come from here to make that into a pi bond. And then the other electron is coming here to this carbon, all right? So the resonance form for that one is going to look like this. Boom, now my pi bond is going to be terminal. And then I'm going to have a radical right here. And everything else stays the same. So we're going to label these C and D. All right, questions about that? Any questions? Any questions? All right. Now, the next step is what?
Termination.
Isn't it the termination?
Termination. Good. All right, let me cut all these because I don't feel like redrawing them. Hopefully I can get, yeah, I got it. And paste that on here. So this is gonna be a termination step. Right? And termination is exactly what it means. It's you're taking the radicals that you made in propagation and you are combining them with bromine to get your product, because that's the goal of the reaction, to put bromine at the allylic site. Is that right? That's why we call it allylic bromination, because we want to take the allylic radical and convert it into an alkyl halide. And there's no, and let me say this too, because this is a common error with this reaction. In the termination step, when you're trying to terminate a radical, you need another radical. All right, you need to combine it with another radical. So we need to combine this with bromine, not HBr. HBr is already paired up. So I don't have an electron to share with the radical in either A, B, C, or D. So I need bromine. I'm saying that because I see this every semester, every time I teach this. It's the same thing. HBr is not, it's present, but it's not a reactant in termination. As a matter of fact, a lot of times, I see you, Brianna. Go ahead.
Yes, I was gonna ask what makes BR more of a radical. Like, I get that it's freestanding by itself, but does that mean that any atom could be a radical?
Yeah, you can convert a lot of different atoms into radicals. A radical, by definition, is just an atom with a single unpaired electron. So you could technically convert any atom into a radical.
Okay, understood.
Mhm. Any other questions about that? So I need those bromines to come in, not HBr, and terminate my radical. So each one of these is going to react with a bromine. All right. This is where my products are coming from. And that's why the reaction is called allylic bromination, because I'm brominating the allylic site. All right, so I'm gonna put this in here. Boom. Those two half arrows. Half arrow means I'm moving one electron. All right. A full arrow like this. Not like that. That's kind of sloppy looking. And that, let me start over. All right, that's a 2 electron arrow. This is a 1 electron arrow. All right. So I'm gonna do the same thing here. I'm just gonna draw it that way. Doesn't matter if you curve it over the top, over the bottom, it doesn't matter. That's semantics. Right, so C and D are here. Same thing, boom, boom, same. Bromine is gonna come in. Those radical, those electrons are gonna be shared in a carbon bromine bond. And that's how I'm gonna get my product. I'm gonna paste. Let me go back and steal one of these things. Steal this one. Right, so that's how I'm getting my 4 products that we predicted. We said at the outset that we'll get 4 products. Is that right?
Yes.
Just paste this up here. I'm sorry for cheating, but this is a lot. Can't wait to use those e-glass boards that we just bought. Paste.
They put him in Armstrong.
We got 3 of them. One of them in 103, one of them in 203, and one in 208, I think.
That's good. I seen that they fixed that little parking booth over there.
Yeah, and they also redid the auditorium too. There's a lot of work about to be done. We got $1 million from the state. So we're about to put in new fume hoods to make sure that y'all can breathe when you're in lab. And we
Dr.
also,
Russell, we're never coming in, are we, for this class?
it's listed as virtual, so I can't change the modality. You understand what I'm saying? If I change it, then I'll get a lot of flack for that.
Oh, I understand.
Yeah. But it would be nice because I do miss being in the classroom. That's the best part of my job, if you ask me. My favorite part is being in the classroom and learning together. Let me there, let me see. Let me here. Zoom in on that, sorry. And then where I have this is terminal. That's what I get for trying to take a shortcut. On me here. All right. So those are my 4 products that I'm going to make by doing allylic bromination on this alkene. All right. So now let's talk about another aspect of this, which is, again, the product distribution. What does that mean? Anybody?
Making different products.
Yeah, it's the percentages or the ratio of the different products. Now we're going to talk about that from a different perspective, because here I want to talk about the fastest form, the slowest, form, and we'll talk about the most stable and the least stable. Come on, Russell, tighten up. I know it's Friday. Least stable. All right. So the fastest form product, somebody help me. If you watch that video on allylic bromination, tell me what dictates, like, or what plays a role in dictating the rate. Anybody?
Is it the symmetry?
Not in this particular case. Right. Think about it like this. Let's say you got a doorway that's 3 feet across. And you got a person trying to come through that doorway that's 6 feet wide. All right.
The amount of constituents.
Yeah, it's the size of the bromine compared to the steric bulk or the steric hindrance on the site where it's trying to get to, right? So if you look at all of these products, you can see right here, that carbon is tertiary, right? This carbon here is secondary, this one is secondary, and this one is primary. Do y'all remember that from part 1? Anybody?
Yes.
Tertiary, primary, secondary just means that the carbon has 3 substituents is tertiary, 2 is primary, 1 is second. I'm sorry. Yeah, 1 is primary and 2 is secondary. So you can see, let me give you an example before we move forward. Right here, this is a secondary carbon. And it's secondary because it has a group on the left and the right of it. So it's got a group here, it's got a carbon here, so it's a secondary carbon. Right, this one up here is tertiary because it has 1, 2, 3 carbons bound to it. So that's what I mean by primary, secondary, and tertiary. All right, so a tertiary radical, even though it's a very stable radical, like when you make it, it's not as reactive, right? Because of the size, well, the bulk around it. So bromine has a hard time getting to that tertiary carbon. So that's going to be the slowest. So we're going to call that A. Y'all want to keep it A, or you want me to call it A1, B1, whatever, or we just leave it A?
Just
Just A.
Just leave it. All right. Okay. Thank you. So A is going to be my slowest form because of the steric bulk at the radical. All right. Does that make sense to you? It's like, again, trying to fit a bowling ball into like a soup bowl. It just doesn't fit, right? And so bromine, being a large atom with a large atomic radius, it is looking for carbons that are less substituted. I'm not making bromine into a real, like a sentient being, but I'm just saying the less substituted the carbon, the faster bromine can get there and react. So which one do you think is going to be the fastest out of all of these?
1 prime.
The primary C, right? So because that's the least substituted radical. Right, C is the least substituted. A is the most substituted. I'm gonna put that in here in parentheses because that's the boiled down terminology that we can use. That's the most substituted. And then stable, the most stable and least stable, that's going to be based on the double bond itself, right? Okay, so when we talk about alkenes, you may or may not remember this, but I'm gonna put that down here. That the stability is based on alkene structure. Right? So the stability is based on the structure of the alkene. So let me show you that real quick. It's kind of alkene stability and carbocation stability are kind of parallel, right? So if I have a double bond that's unsubstituted, meaning everything on it is hydrogen, and then I start adding in substituents. This is mono. I'm just going to abbreviate substituted. That's my least favorite word in the whole English language. All right. I hate spelling it and I hate saying it. So this is di substituted. And then if I put 3 groups on there, this is tri-substituted. And if I put 4 groups, oh, sloppy, sorry. This is tetra substituted, right? So alkenes do that, right? So the stability of the alkene is increasing as you increase it, as you increase the number of substituents around the alkene carbons. So stability, let me see, hold up, I know what to do. Come on. Let me shrink this down so I can put an arrow over here.
Why is it more stable when it has like
More
other
substituents.
substitutes on it? Yeah.
I like those kind of questions. Because now we can talk about something technical, right? Think about the hybridization state of the carbon in the alkene, like right here, these carbons are sp2. And so what happens is, do y'all remember from part 1 when we talked about percent S character and how it affects electronegativity? Anybody remember that?
I remember talking about it.
So the sp2 carbon is a little more electronegative. So you actually have a little dipole. That was here, right? So those carbon-carbon sigma bonds kind of donate electron density to the sp2 hybridized carbons. And so the more you put around it, the more electron donation is happening. So it's kind of satisfying that electronegativity of those carbons. So that's why the more substituents you put, the more stable that alkene is going to be. So this is increasing stability. Right? So the stability is increasing as you increase the number of substituents on the alkene. Right, so as the number of substituents increase, so does the stability. And it's based on that idea, almost like it's similar to what we learned about carbocations. Do y'all remember the term? Probably not. Well, maybe, let me not underestimate you. Hyperconjugation, anybody remember that term? No?
No.
Okay, so all that term means in layman's terms is the donation of electron density from sigma bonds. So sigma bond, carbon, sigma bonds can inductively donate electron density towards electronegative atoms or carbocations, or even a carbanion. You can have if it has too many substituents, it's going to be less stable because of the same phenomenon that you donate electron density towards that center. So that's what these dipoles indicate. That these carbon-carbon sigma bonds are donating electron density. All right. So let's go back up here and look at our products. Which one of those alkenes is the most substituted out of all the alkenes? Look at, now we're talking about the double bond now. All right, so don't confuse that with where bromine is. Now we're talking about the alkene, which is here, 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 and here.
The
What do you
second
think?
one.
So would it be secondary?
Which one? You talking?
The
Yes.
bottom one?
B. Are you talking about B?
Oh no, I wasn't. But yeah, sure, B.
Oh, no, you can't. No, I'm just joking. Yeah, it's the one that you get from B. Do you see the alkene right here? How it's tri-substituted?
Yes.
It's got 3 things attached to it, right? It's got a carbon here, and another carbon over here.
Mm-hmm.
Yeah, so that's going to be tri-substituted. And then this one, D, is mono-substituted. And then both A and C are di-substituted. So your more stable product is going to be B. Let me shrink that because I don't want this looking crappy when you get ready to go back and look at the notes. Because it's a more substituted alkene. All right, and then by that same token, D is going to be the least stable because it's the least substituted alkene. All right. Questions about that? So the fastest is gonna be the least substituted site. And then fastest form, slowest form is dealing with the site where the radical is. And more stable and least stable is based on where the alkene is, like the structure of the alkene. Let me put that up here too in parentheses. That's based on the structure of the radical. All right, any questions about that? All right, we actually only got like 3 minutes left, so I don't want to start another problem. So on Monday we're going to do alcohol conversion, but I want you to work on this one on your own. If you get stuck, ask a question, and then also this one. It looks like an X. All right, you should be able to do this problem based on what we've done already. You should be able to, at this point, you should be able to identify allylic sites. You should be able to predict the number of products. Right, you should be able to rearrange allylic radicals by resonance. And you should be able to show the mechanism. Right, we've been through that mechanism about 3 or 4 times. So you should be able to at least figure out which sites are allylic and predict the number of products. And you should be able to draw the products. All right, so I want you to work on those other 2 on your own. And if you don't finish them or if you get stuck, just ask a question. I'm happy to help. And now, so on Monday, we're gonna start with alcohol conversions into alkyl halides. All right, and I'll send you a really short video about the radical mechanism, just to kind of help you to think about that propagation, initiation, propagation, and termination, those steps. All right, any questions? Everybody good? 30 people here today, and we're down by 10 people. That's not good. All right. If there are no other questions, I'm gonna stop. Let me stop the recording.